Alright, welcome to the NUPOC video study guide number 103. Let's take a look at another geometry by calculus problem, and this time, instead of just deriving an area or volume, we're just going to go ahead and use integration to find the center of mass along a 3-meter thin rod that has this density function here. Rho of x equals 1 plus x over 3, and the units on density, right, are kilograms per meter in this case, since we just have a thin rod, right? It's not kilograms per square meter, which it would be if we had like a thin plate or a thin sheet. And of course, if we get a 3D object, it would be kilograms per cubic meter or kilograms per cubic centimeter or something like that. Alright, so let's draw out our geometry here. So we have this thin rod, and we're going to say it starts at x equals 0, and it's 3 meters long, so it ends, we're going to say at x equals 3, I'll say x equals 3 meters here, I'll say x equals 0 meters, right? And the density function, rho, right, I'm going to write it out again here, 1 over x, 1 plus x, 1 plus x over 3. Make sure we get that right. Rho of x, we can even turn that into an x and then write another rho here. Yeah, there we go. Alright, rho of x equals 1 plus x over 3 kilograms per meter. And so we want to find somewhere there's going to be our center of mass, right? Or what we'll call that x bar, right? X bar is sometimes used for centroid, which is sort of the unweighted geometrical center, or the geometrical mean of a shape, whereas center of mass, right, is mass weighted. It's like a mass weighted average of the center of an object. Okay, so we can say that x bar, right, which is our center of mass, right, equals the moment about the y-axis divided by the total mass. So this is mass, this is moment about y-axis. So if we're looking for x bar, why are we using moment about the y-axis? Well, if this is our x hat direction and this is our y hat direction, right? Well, x bar determines how this shape would rotate about the y-axis, right? Because it's laying on the x-axis itself. So if my pen, right, is the y-axis, and this is some plate or sheet or something, my hand right here, right? The distance of the x component of the center of mass will determine how it teeters on the y-axis, right? Conversely, if I wanted to find what the y-center of mass is, I would be concerned with how the shape teeters on the x-axis, right? So that's why we use the moment about the y-axis when we're looking for the center of mass in the x direction. Alright, so first we have to find what's the total mass of the object, right? And we have the density function. So for that, we can just go ahead and integrate the density function, right? Rho of x dx from 0 to 3, and this will be the total mass, right? And so this ends up being integral from 0 to 3 of 1 dx plus 1/3 integral 0 to 3 of x dx. Okay, we're not going to go through all the integration detail because we can all obviously do that at this point. So this right here is going to come out to be 1.5 kilograms. It's going to be the units on that. since we have rows in kilograms per meter, and then we're integrating over meters, right? This right here is just going to come out to be 3 kilograms. So the total mass is 4.5 kilograms. Okay. Now what's the moment about the y-axis? Well, for that, all we do is we add an x-coordinate in front of our density function rho of x, and then perform the same integration. So this will be 0 to 3 x rho x dx, right? So this x is going to get multiplied into or distributed into each term of the density function. So that means we will end up with the integral 0 to 3 of x plus x squared over 3 dx, and then we can split that into two integrals. Integral 0 to 3 of x dx plus 1/3 integral 0 to 3 x squared dx. Again, we don't have to go through every integration step, but we can say that this, right, this is the same as the, almost the same as this integral up here, except it doesn't have the 1/3. So this is going to end up being 3, right? And this right here is going to end up being, excuse me. This right here is going to end up being x squared over 2, and then we evaluate that from 3 down to 0. 3 squared is 9, so it's going to be 9 over 2. So this one is going to be 4.5, right, kilogram, and now it's actually going to be kilogram meters, because we have kilograms per meter times meters, and then times meters again, because we have this factor of x. This integral right here is going to become 3 kilogram meters. Alright, now let's go ahead and divide my by the total mass, right? So the total my, let's write it over here, is going to equal, right, 7.5 kilogram meters. So my over m, which is our center of mass in the x direction, is 7.5 kilogram meters divided by the total mass, which is 4.5 kilograms. The units of kilograms obviously are going to cancel, and this ends up being 1.67 meters. So our center of mass in the x direction equals 1.67 meters. So if we looked at that on this figure here, that would be right there, right? So we go 1.67 meters from the origin, and that's where we would be able to balance, this rod with this varying density. So thanks for watching, and as always, don't forget to click to subscribe so you don't miss out on any upcoming videos.